So good morning. Today I will discuss two important reactions. One is called reversible first order reaction, and as you know that you have already learned the rate change of extent of the reaction with respect to time at constant temperature and volume. Then you know rate constant and the relationship between the rate, or sometimes it is concentration, and rate constant. It is called the rate law. So this is the simplest reaction first I will discuss, and little bit mathematics is required for that. So you can call it is a role of elementary mathematics for solving some kinetics problem. Basically we will use some simple formula of the integration, some simple formula of the differentiation. So let me start with the very simple reaction, and that is A is converted into B, and of course, as I told you, it is a reversible type of the reaction, and we can write this rate of forward reaction and opposite it rate of reverse reaction. You can write K1 also, even K inverse also. But I am using Kf and Kr. Now the first step is very simple, that is rate of change of reactant. Very simple, because the concentration is decreasing, so therefore I have just put a negative mark, minus. It of course depends upon the concentration of the A, so I can write Kf A. Very simple. Because it is a reversible type of the reaction, after calculating the Kf and Kr, you can predict the things. But before experiment, it is very difficult for you to know that which step is fast. There is a possibility that Kf is greater than Kr. Or also it is also possibility that Kr is greater than Kf. That is different thing, but normally. So I can write like that. Kr, so B, which is a very common differential equation, because we would like to know the change in concentration of A with respect to time. But the problem was that there are two variables, A and B. So integration of this is difficult. So therefore independently what we can do, we can transform the B into A. That means suppose there is a one variable, so that will be very easy to integrate. Now why integration is required? Because we are measuring the rate constant, so we would like to know that how A is converted into B, the change in concentration. It may be slow reaction, it may be fast reaction. So what we do, as you know that there must be some initial concentration. So that is A, starting point, and it is equal to A. If the reaction is very slow or the reaction is fast, then of course there is a possibility of B. Why we are using simple mathematics? Because it is easy to transform the B into A, because there is only one variable. So I can write like that, B is equal to A0 minus A, one type of concentration. So we can substitute the value of B in this equation. So I can write like that. Even you can do same thing. If you want to write d by dt of A, so minus kf like that, then plus B. That is also possible, but it is better to use this type of things. So I can write like that, kf A minus kr A0 minus A. Now whatever we are doing, that is before equilibrium. Bear in mind, before equilibrium. Many times I am telling you that this is the simplest case, and if you understand this thing, any type of reaction, maybe a consecutive type of reaction, parallel reactions, or any other complex reaction can be solved because the methodology is same. But of course, different types of mathematics is required. Otherwise, but the method is same. First you have to write the differential equation, then you have to integrate it, and you will get the final result. That is the objective. So if I write like that, so I can write here minus d by dt of A is equal to, now very simple, that it is kf A. So if I do it like that, it will be plus, so I can write kf plus kr A minus kr A0. Now again there is a problem. Now our part you all know that we have to integrate it, whatever it is. So again there is a problem because there are two rate constant. Of course this is a constant. So what I do, I want to simplify it. So sometimes it is called in chemical kinetics mathematical simplicity. Mathematical simplicity. So suppose I think this is K and A is suppose F. So I can write like that, Kf is equal to F, complete F, full equation. But again there is a, so it is a constant. Of course there is another constant. Kf, sorry, we should like that. This is K, F is this minus, because that is also there. Suppose it will remain constant. As I told you, that transformation from one variable to another, that is equal to F. Okay. Here is also I can write like that. Okay. This is capital K, which is the composite of Kf and Kr. So if the derivative is like that, it is a constant. So a df derivative constant, no problem. Df. So you can write that, and because large number of biology students is here, so for them I am just solving very simple. Mathematics students can direct solve it. Capital K. This is not small k. So now you substitute the value of here. So you can write like that because it is df by dt. So df is equal to df k dt here, of course minus, is equal to the whole f. That is mathematical simplicity. Now rearranging, rearranging these things. So it is like that, minus df is equal to k dt. Now any student can solve it because you all know that dx x, what is the value? Log x, natural log x, like that. 1 by x dx, like that. So it is also same thing, so I can write like that. And if I integrate it from 1 to 2, 1 to 2. Why it is 1 to 2? Because with respect to time, the A is gradually converted into B. So everything I am talking about the before the equilibrium, not after the equilibrium. So if it is, you know that it is natural log of F2 final minus F1 is equal to capital K. It is a definite integral. You must know the difference between indefinite integral and definite integral. Very elementary, a very elementary thing. Very elementary thing. So now there is a minus sign, and if t is equal to 0, so I can write natural log of F1 F2. Why? Because I change this minus sign. So naturally F1 F2 is equal to K T2 minus T1. If t is equal to 0, that is starting point. So we can write natural log of F0 divided by F is equal to K and T. If you remember your school days or in college days, you will get the things. And now if we substitute the value of F in our main equation, that means F is Kf plus Kr A minus Kr A0, that is F. So 0 divided by F, so it is very simple because the starting point, then gradually we will go to the consecutive reactions and little bit difficult reactions. So I can write like that. So last step, natural log of F0. So you can write everything Kf plus Kr A minus Kr A0. Everything divided by like that. F2 by F1. So natural log Kf, Kr is cancelled with this. So Kf A0, because it is starting point is 0, na 0, 2. So final equation is Kf A0 denominator, same thing, because F0 divided by F, this Kra is cancelled, so Kf is 0. So it is Kf plus Kr A minus Kr A0 is equal to capital K and T. But this is not the end of the story, because this is a reversible first order reaction. So equilibrium is very important, where rate of forward reaction is equal to rate of backward reaction. So therefore we have to just modify this equation to get the final equation. So what we do, now, we can write like that. It is like Kf A equilibrium, you see, is equal to minus Krb, or like that, same thing. So what we have written here, so it is actually Kf AE, same thing minus, you can write like that, Kr A0 minus AE. Equilibrium is there. So what I can do, it's same thing, Kf plus Kr A equilibrium minus Kr A0, or even you can like that. So this is the at equilibrium. So now I am getting a different reaction, not different reaction, but equilibrium. It is subscript super E. So now I can solve the problem, because now I am getting the value of Kr A0. So now you can understand the things. This is our equation, Kf Kra. First equation is like that. This is our first equation. So therefore, again same thing, minus d by dt of A. This is the final step. So in place of K0 we can write like that, Kf plus Kr A E minus, now you know the value of Kr A0, so it is Kf plus Kr A. No, it was A. Again, I'm sorry. Right. It is A. Because these are first equation, these are first equation. These are first equation. That is combination of A and A0. Apply equilibrium, we'll get the value of Kr A0. So last stage, that same thing, just like you have written Kf, Kr common. So A, suppose the whole thing is A, whatever it is, AE. Sorry, again, always equilibrium must be written in subscript, superscript. This is called the subscript, it is called the superscript. So same thing, you just again rearrange this equation, that means again minus d by dt of A divided by this whole, you can write like that, A minus A, or it is suppose same thing like that. And again here is Kf and Kf plus Kr T. So same integration, same way, if we do same type of things, A by A, dx by x, same thing, log x. We assume this whole thing is A minus A0 is by a dx, but this is suppose A. So you will get, I have only one solvable equation. I will get natural log, same thing, A2 minus A1. There is a minus sign. So I can write A1 A2. Same thing at T is equal to 0. So you can write A0 and A. Initial or final, or sometimes in some books it is written like the T, total concentration. You can write T. So same thing. So natural. Now you substitute the value of A0, that is A0 minus AE divided by A minus AE is equal to KT. This is capital K. Now you remember, if you plot a graph between this left hand side and T, you will get the slope value is the SLET constant. Now you assume, last step, that if it is combination of KF and KR, just you imagine about your B.Sc classes, very common equation, that if the value of KF is greater than KR, so in reaction the possibility of B will be very high, because KF value is very high. That means whatever B is formed, it will remain in the solution, and if KR will be very high, so that B, whatever B is produced, it is again converted into A. So most of the cases it depends on, unless until you determine the forward reaction and backward reaction. So then that equation, the simple equation, because if there is very high quality of B, sometimes A, whatever A is equal to A0, like that. So finally you can see A divided by A0, your school level equation, minus KT. I think now you can remember this thing, that A is equal to A0 epsilon KT, like that, this equation. So this is the simplest equation we have solved it today, and this is the example of first order, or you can call it as a reversible first order reaction. And sometimes it is called, because this is the most simplest. After this reaction we will solve the second, A plus B is converted into B. That is simple dx by dx integration will not be useful. Then we have to apply some of more, not complicated mathematics, but more example of these things. And in your course you have to first start with this simple equation, then parallel equation, then opposing reactions, then consecutive type of the reaction. So in my next class I will explain the second example, that is here I can write. Today I will not solve it. Tomorrow or day after tomorrow, Saturday, I will solve it. But you can prepare it well in advance, and you will see that A plus B, as I told you, is the product. At that time we have to use different types of, suppose dx, then x, p plus x, like such type of integral, or 1 by like that. So we have to solve it, minus 1 by p natural log. I'll explain. That means we need a little bit mathematics to solve this type of. So finally I should tell you that whenever we discuss with the chemical kinetics, so little bit knowledge of integral calculus is required. Similarly, when you will study the thermodynamics, then little bit knowledge of differential calculus is also required. And when you solve the consecutive reaction, that is A is converted into B, B is converted into C, simple integration will not be required. Therefore, we have to use certain different types of things. And that time, differentiation is slightly different, and differential equation is also. Sometimes we want to know how one derivative change with respect to other. So, thank you very much.